Welcome back, class. I'm Dr. April Ström, and I wanted to continue talking about this wonderful CAR A and B task that I just set up. But here, what I've done this time is now I've assigned equations, functions, for each of the cars. So let's imagine that the graph of car A was depicted by this equation, y equals square root of x. And let's imagine that car B, the blue graph, is described by the equation y equals x squared. Now we have a couple of functions that we can try to use with integration techniques to figure out what this shaded region is between these two curves. Now, often the problems say something like, find the area between this curve and this curve. And so, of course, what you'd want to start out with is the graph, find what the shaded region is that it's describing, and then go from there to set up your integral and then finally integrate by hand if you can. So we already have the graphs for us since this is part of the car A and B problem. So let's set up our integral. We've established in the last video that our objective here was to find how much further car A traveled than car B, because we decided that in fact car A went further since the area under car A's graph was a larger area than the area under car B's graph. And to find really the difference between those areas tells us what this region here shaded in purple actually represents. So what we need to do is create an integral. So this is, of course, describing our area. And what we would like to do is imagine like us taking little slices of this region, and then we're going to find the areas of those slices and sum them up. Remember, with integration, we are summing up stuff, and the stuff here is going to be those slices along the way. And of course, we want an infinite number of slices. So we have an integral here, and our boundaries are going to be starting from 0, since that's the point of intersection, one point of intersection of these two curves. And also the next point of intersection is at 1. So we want our boundaries of integration to go from 0 to 1, since those are the endpoints for the region that we're interested in summing up. So we have an integral from 0 to 1 of, now we have to think here. Okay, so once again, we have first the big region for car A going all the way down to the x-axis, and then the smaller region for car B also going down to the x-axis. We essentially want to take the larger area and subtract off the smaller area to reveal the purple area here that's quote unquote between those two curves. So my integrand needs to start with the bigger area first, which is modeled, the curve itself is modeled by the function square root of x. So we start with our square root of x here, dx. So that representation tells us simply the area under the car A's curve. And then we're going to subtract off from that the area, right? I'm going to do the integral, so I'm summing up all the little slices and the areas there. And so I also will have the boundary 0 to 1 for that integral. And now this, I need to create an integrand for the smaller area, the area underneath the curve for car B, which is defined by x squared. So now I have an x squared dx. Okay, let me pause for a second and just remind you, why are these the areas? This would, like I mentioned, essentially be the area for car A. And why is it area? Well, we technically have two things being multiplied here. First of all, remember I said we're having slices. Well, the slice height is defined by square root of x. That tells us how high will each of the slices be. dx tells us how wide each of the slices will be. Well, recall in integration here, we're thinking about those slices as being infinitesimally small, like super skinny. But we're really taking each of these slices as kind of like super skinny rectangles. They have a height, in this case of square root of x. They have a width, which is dx. When I multiply those together, I get an area of that slice. That's a single slice, but then I want to add up all the areas of those single slices for an infinite number of slices between 0 and 1. So that gives us the area for car A. Now let's shift over and just analyze this second integral, because this should represent the area for car B. Here, once again, I have all these slices that I need to find the area of, and then I have an infinite number of those slices that I'm summing up. Well, each slice will have a height of x squared and a width of dx. Remember, infinitesimally small width. Multiply those two together, that gives us the area of all those slices, and now we're going to integrate, so we're going to sum up all of those, in fact, infinite number of slices between 0 and 1. So we have the area for car A, and now we're going to, which is the bigger area, and now we will subtract off the area for car B. Thus, the difference between those will give us the area of interest, the fact that we want the area between these two curves. And once again, that will actually represent how much further car A traveled than car B. So let's carry out the integration here. We still have, I like, by the way, to keep writing that this is area. It just reminds me that that's what I'm trying to find. So I'm going to say area equals. Now I do have two distinct integrals here. I could make a choice. I can decide to integrate separately each one, or I can merge them together to be one integral with the two functions being subtracted. And that's the route I'm going to take. So we have an integral from 0 to 1 of square root of x minus x squared dx. So this subtraction will tell us all of these slices and their different heights along the way, but then multiplied by this infinitesimally small rectangle for the slice. So now we continue on with our integration process, and you might notice that in fact when I need to take the integral of this term, square root of x, it might be really nice to have that as a power. So how about we just rewrite right now, instead of square root of x here, how about we write that as x to the 1/2 power and then minus x squared. I'm going to integrate those terms separately, but it's really to our advantage to take out the roots and put in the fractional exponents. Because hopefully you recognize that all we have to do here is the reverse power rule. So as a reminder, to reverse the power rule for derivatives, because we're integrating, what we would do to find the antiderivative is we would add 1 to the power that we have here, then divide by new power. So I have a 1/2, here's my x. I had a 1/2, I'm going to add 1 to that power, but I'm going to now divide by my new power. So 1/2 plus 1. We can simplify here in a moment. And then I will repeat that kind of process, but with the x squared. So carry down my subtraction. Now I have x squared, reverse power rule there. Let's add 1 to the power. So I have x squared, but plus 1, divide by new power. But then I have to recall that I was integrating between 0 and 1. So I'm going to use the fundamental theorem of calculus to help me evaluate my antiderivative at those boundaries. So I will show that by saying I'm going to evaluate this particular function here, my antiderivative, between 0 and 1. So let's clean this up so that we can actually do the evaluation. So we have area is equal to, here I have x to the 1/2 plus 1, so that's x to the 3/2 power. So x to the 3/2 power, but all divided by 3/2. How about we just go ahead and reciprocate that and throw it out in front? So I could divide, let me just show you this. I could divide by 3/2, but quite frankly, that's the same thing as multiplying by 2/3. So how about we just do that so we don't have that fraction to deal with? So we have our x to the 3/2 power, that still stays 3/2, but the coefficient in front of the x becomes 2/3. So 2/3 x to the 3/2 power, but then minus, similarly, we have x to the 2 plus 1, so x cubed divided by 3. I don't need to reciprocate and all that, but I can move the fraction out in front as its own coefficient. So I think I'll write that as 1/3 x cubed. Why 1/3? There was a 3 in the denominator, and so I just pulled out to the front 1/3 x cubed. Of course, still evaluated at 0 to 1. And so, like I mentioned, what we now need to do is use the first fundamental theorem of calculus to evaluate this expression, this antiderivative, at 1, then subtract off the evaluation at 0. So I'll write that out. We have area is equal to, I'm going to first evaluate my antiderivative at 1. So I have 2/3 times 1 to the 3/2 power minus, and then here I have 1/3 times 1 cubed. That's just the first part, evaluating my antiderivative at 1. But per the fundamental theorem of calculus, I now need to subtract off a similar process, but when I evaluate at 0. So I now have 2/3 times 0 to the 3/2 power minus 1/3 times 0 to the 3rd power. Well, what's really nice is if you look carefully over here, 0 to the 3/2 power, still 0. Times 2/3, still 0. Minus, over here, 0 cubed, still 0, times 1/3, still 0. This whole thing in brackets is just 0. So we don't have to worry about that so much. Right here, what I end up with is 1 to the 3/2 power. Well, that's just 1, times my 2/3. So I have my area is equal to, so this piece will give me 2/3 minus, over here 1 cubed is still 1 times the 1/3. So now I have that my area is 2/3 minus 1/3. So when I simplify that, I end up with the final result of area is equal to 1/3. Now you might be thinking, well, 1/3 what? Okay, let's go back to the original problem. Remember, we were given velocity in miles per hour. We have traveled for exactly 1 hour, and our velocities apparently, magically, were modeled by these wonderful functions, y equals square root of x and y equals x squared. And so if that all were true, then essentially this area reveals to us how much further car A traveled than car B in that 1 hour time span. Well, using distance of miles, because that is our distance measurement here, we would label this here as our 1/3 miles. We would say car A traveled 1/3 of a mile more than car B in that amount of time, 1 hour. And so we can use integration to find that area between curves, but this happened to be an example within context to kind of make meaning of what's happening with these cars relative to the areas under each of the curves and then the area between those two curves. So I hope this video was helpful. Please be sure to like the video and also subscribe to our channel. Thanks.